Hi, I'm Yutaro Omote. I'm going to present our work Transformer-based approach for predicting chemical compound structures. First, we introduce the background and an overview of our approach. Then we are going to propose methods, experimental settings, and results. Finally, we conclude this presentation. First, we introduce our research motivation for prediction of chemical compound structures from chemical compound names. Knowledge of chemical compounds is necessary for developing new materials and drugs and for synthesizing products from new materials. This is an example of chemical databases. Databases contain information of chemical compounds, such as physical properties of chemical compounds. Currently, chemical databases are manually maintained, which consumes much time and cost. Therefore, automation and assistance database creation for chemical compounds is required. Information extraction technologies, such as named entity recognition, relation extraction, and entity linking, are used to create databases for chemical compound from text. Named entity recognition recognizes basic information of databases such as chemical compound names and numerical values. Then relation extraction identifies relations between chemical compounds and numerical information. Entity linking is used to identify chemical compound names, which indicates the same entry in the chemical compound database. However, there is an alias problem of chemical compounds for information extraction. The problem occurs because each chemical compound has several notations. For example, this chemical compound has several notations, such as methylbutyrate, methylbutanoate, butanoic acid methyl ester. Moreover, new chemical compounds are being discovered at every moment, and database registration of chemical compounds has not caught up. It is said that several billions of chemical compounds exist, but only a portion of these is registered in chemical databases. Even PubChem, one of the largest databases of chemical compounds, includes information of only approximately 111 million chemical compounds. Therefore, we think it is difficult to use a reference-based approach that consults dictionaries or databases for solving alias problem. However, there is a unique characteristic that conventional named entities don't have. Each chemical compound has its unique structure. In other words, if we can identify chemical compound structures of chemical compound names correctly, we can identify the same chemical compounds denoted by different notations. In this work, for chemical information extraction, we tackle prediction methods of canonical smile strings from chemical compound names. Canonical smiles is a representation format of chemical compound structures. We first predict chemical compound structures from different chemical compound names. If we have the same smile string, we regard they have the same chemical compound structure, and we think their names are equivalent expressions. There are various chemical structure representations, such as graph, canonical smiles, and inch. We use the canonical smiles representation for the chemical structure prediction because it is simpler than graph and inch strings. And there is almost one-to-one correspondence between graph structures and smile strings. Therefore, smiles is sufficiently representative for creating a chemical compound database. Conventional tools employ rule-based methods for predicting chemical structures from chemical compound names. Although rule-based conversion can accurately predict the structures of chemical compound based on systematic nomenclatures, such as the International Union of Pure Applied Chemistry (IUPAC) nomenclature. It often fails the structure prediction of chemical compound names that violate these nomenclatures. This table shows prediction performance of rule-based methods for each name type. Note that the synonyms category includes non-IUPAC chemical compound names. Here, I introduce our methods. To improve the law prediction performance of compounds categorized as synonyms, we propose neural network-based models that predict chemical compound structures represented as canonical smiley strings from chemical compound names. In this work, we use a transformer-based sequence-to-sequence neural network model for machine translation, which achieves a state-of-the-art performance in various tasks among the sequence-to-sequence neural network models, such as recurrent neural network-based models. To improve the conventional transformer-based model, we introduce the following two chemical structure-oriented features: a loss function considering the constraints on the number of atoms of each element in the chemical structure, and a multitask learning for predicting both smiley strings and inch strings. The transformer-based model predicts smiley strings from chemical compound names, so its input is a chemical compound name, and its output is a smiley string. During the learning process, this objective function is minimized. We improve the conventional transformer-based model by introducing two features. First, we propose a softmax-based loss function that constrains the number of atoms of each element. The model is trained to minimize the difference between the number of atoms of each element, such as carbon, oxygen. For example, for this predicted smiles, it has 4 carbons and 1 oxygen. And for this correct smiles, it has 5 carbons and 2 oxygens. The difference is 1 carbon and 1 oxygen. The model is trained to minimize this difference. The loss function under the proposed constraints is given this equation. This is the number of atoms of each element in a correct smiley string, and this is the number of atoms of each element in a predicted smiley string. The probability distribution of the number of atoms of each element is obtained by using Gumbel softmax. The objective function under the proposed constraints is defined as this equation. This is the loss of constraints on the number of atoms. This is a hyperparameter that controls the degree of considering L atom. This is a loss of the name to smiles prediction model. We also propose a multitask learning methods that shares the encoder of the name to smiles and name to inch prediction models and trains both models at the same time. Int is another string representation of chemical compound structure. The proposed multitask learning minimizes this objective function. This is the loss of the name to inch prediction model. This is a hyperparameter that controls the degree of considering L inch. Next, I'd like to talk about experiments. We created a dataset from the dump data of PubChem. The data comprised pairs of a chemical compound name and a correct smile string. We selected chemical compound names that were categorized as synonyms. We compared our methods with rule-based conventional methods. Conventional methods are Option, which is a rule-based browser that generates smile strings and inch strings from chemical compound names, Tool A and Tool B, which are commercially available tools. Proposed methods are transformer-based prediction of smile strings from chemical compound names, training with constraints on the number of atoms, and multitask learning for predicting both smile strings and int strings. Chemical compound names were tokenized by a BP-based tokenizer. When tokenizing the SMILE strings, each element, for example, C, O, Cl, identified via regular expressions, was regarded as one token. The remaining symbols not covered by regular expressions were divided into single characters, each regarded as one token. For tokenizing int strings, the model was learned on sentence piece, a unigram-based unsupervised training methods for word segmentation. Hyperparameters of transformer model followed transformer-based ones. The hyperparameters of training and inference were as shown here. Then I'd like to show experimental results. This table shows the experimental results. Transformer-based ones are our proposed methods. The notations BPE and OpsinTK indicate the use of the BP-based and Opsin tokenizers, respectively. OpsinTK plus BPE uses BPE if Opsin tokenizer succeeds. Otherwise, the model don't generate SMILE strings. In the rule-based methods, Opsin achieved the best F measure around 0.758. So we compared our models with Opsin. The conventional transformer-based model achieved higher F measure than Opsin by 0.041. The proposed constraints and malicious learning attained higher prediction performance than the existing rule-based methods and the conventional transformer-based model. Each gen with BPE showed 0.056 points higher F measure than Opsin. The highest F measure and precision 0.829 and 0.886 were achieved by each gen with OpsinTK plus BPE. We measure the Jaccard similarity between each structure that was incorrectly predicted by each gen with BPE and correct structure. The Jaccard similarity, a common technique for measuring chemical compound similarities, is defined as this equation. This figure is a histogram of the Jaccard similarity scores obtained in this analysis. We find that most of the incorrect SMILE strings generated by each gen with BPE possessed high Jaccard similarities to the correct SMILE strings. The average Jaccard similarity was 0.753. This figure shows that an incorrect structure generated by each gen with BPE is compared with its correct structure. The two structures differ only by whether methanetol or ethyl-sulfonylbutane was bonded in the partial structures enclosed by the red ellipses. In other words, the two structures are very similar. Finally, I'd like to give conclusions. We introduced transformer-based prediction methods which convert chemical compound names to SMILE strings trained with constraint of the number of atoms of each element in the SMILE string. We also propose malicious learning approach that simultaneously learns the prediction to SMILE strings and int strings. Through the experiments, our methods achieved higher F measures than the existing methods. In future work, we intend to explore various tokenization methods and further improve the prediction performance. We'd also like to apply the proposed loss function to malicious learning. We release the dataset used in this work in the following web page. Thank you very much.